Here we're looking at an Atwood machine with friction. We're looking at a pair of inclined planes with two boxes that are connected by a rope and pulley. So we're given the masses of the two blocks, negligible mass of the cord, meaning we can ignore the cord other than the fact that it transfers the tension from one block to the other. We're given the coefficients of friction, and we're told the pulley is frictionless and negligible mass, meaning that it is only serving to redirect the direction of the tension force. It's not actually contributing to the system. We want to find the acceleration of the system. So we want to find how fast the system is going to move one way or the other. And in this sort of situation, when we're told about the masses of the objects lead to acceleration. They also lead to gravitational force. We're told about the coefficients of friction, which is frictional force, and we're told about the rope, which tells us about tension. Then what our plan here, what our expectation is that we're going to look at the sum of the forces, and that will equal mass times acceleration. So a lot of the information we're given is about finding forces. If we can find all the forces, we can find the acceleration of the system. We know that if these two blocks are connected by a rope, there's got to be one acceleration for the entire system, that they will move together. The trick here is that depending on the two blocks, how big each block is, and how steep each ramp is, this system could move to the left or it could move to the right. And it's hard to say, particularly here, because you have a lighter block on a steeper ramp and you have a heavier block on a shallower ramp. It's hard to say which one will dominate the motion. And then the further problem to that is looking at the friction. That friction always opposes motion, and so we have to look at what direction that motion ought to be before we consider friction. So one method that we can use is to look at what I call the natural motion of the system. That if we ignore friction, we look at what direction the system would want to go just on its own without friction. And then what we can do is then include friction and see if the friction is very strong, which means that the friction would totally stop and shut down that natural motion, or if the friction is relatively smaller than the other external forces acting on the system, then the friction would just slow down that natural motion. But if we don't know what direction the system is going to move, we don't know what direction right now to give to the friction, what direction that friction should be pointing in. So when we're looking at the forces on the system to find the natural direction, we can just look at each block and see how each block is going to act. We don't have any information about what direction it's going to go, so we really just need to pick one. So let's go with the big block, and we'll assume that the big block is going to slide down and that the smaller block will be pulled upwards. This is the acceleration constraint, that if this block goes to the left, that block also has to go to the left. Their magnitudes of the accelerations will be the same because they're connected with the rope, even though the directions of the accelerations will be different. So we can start by looking at the first block. That block is going to have gravity acting down on it. That block is also going to have tension pulling towards the rope, towards the middle of the rope. And that block is going to have a normal force acting on it. Now, if we put our axes the way that we often do when we have an inclined plane, we see here for moving up or down the plane, we're only moving in the x direction. There are y components here. Those y components will cancel themselves out because we're not going to come flying off the inclined plane. We're going to continue to move along the plane. And so we can break this into components, and we have a we have perpendicular and parallel components to include here of the gravity. Now, if we're assuming that the acceleration is down the inclined plane, that acceleration is to the left, and so that's negative. So when we want to write out Newton's first law, we'll write that mg sine theta is down the hill, down the inclined plane, that's to the left, so that's negative. The tension is pulling it up, which is to the right, that's positive, and that is equal to the mass times the acceleration, and the acceleration is negative because we're sliding to the left down the hill. We can do the exact same thing for the second block. We again have gravity acting on it. We again have different components. And we again have our normal force and our tension force. And so we can write Newton's second law for this block as well. Again, we're assuming that we're following the convention for our coordinates. We use to the right is the x direction, up is the y direction, and we've just tilted them to match the incline of the plane. So in this case, we have the tension that's pulling us along the plane, that's to the left, so that's a negative amount. We have the force of gravity, which is to the right, so that's positive, and we have the, and that is equal to mass times acceleration, which is to the left, so that's negative as well. So this way, by using the negative sign to show the direction, that means that this A is just the magnitude of the acceleration. What we can do here, as we often do, we're going to add these two equations. The reason why we do that is when we add the two equations, the tension and the negative tension cancel out. That's an internal force that we don't know anything about. We can multiply through with a common negative sign to get rid of that, and then to find A, we'll factor A out of here and divide, and we find this. Now when we plug in numbers, we can plug in numbers, and we're interested in whether this is a positive or a negative number. And what we find is that this is actually a negative number. All that means is that what we assumed about the acceleration over here was incorrect, and in fact the acceleration should go back the opposite direction. That in fact will be going this way. What that means as well is that means that for each individual block, it means that this block, the block 1, is going to the right, and that this block 2 is also going to the right. And what that means for us then is that when we include the force of friction, the force of friction will be to the left in each case. And the same over here. have a tension, and we'll also have a force of friction. Now, what this means for us specifically is we've done a lot of work. We don't want to throw all of that out, and we don't have to throw all of that out. We'll erase what we have, the end part of what we have, and basically everything that we have here is still correct. We've changed the direction of the acceleration. We have not changed the direction of any of the forces. The forces are still in the same directions relative to our coordinate systems. We just found out that the magnitudes of the forces, basically that tension is greater than the magnitude of this force, and that this force is greater than the magnitude of the tension, so that our accelerations end up being positive. What they also mean is that we have these forces of friction, and both of them are to the left. And that means that both of them should show up when we sum up the forces. And both of them should be negative because they're both pointing to the left. Now, the last part is to say we don't know what force of friction there is. It could be static friction and it could be kinetic friction. What we have to look at is see the static friction means it's not moving at all. There's a maximum amount to that, and if we look at the, what we have to look at is look at the overall forces acting on the system. If those forces are big enough to overcome static friction, then it means we have to use kinetic friction. If these forces of static friction are too big, it will stop all of the motion, and we'll test that right now. We'll do exactly the same thing as we did before. We will note that each one of these forces of friction we're going to begin with a static friction and test that, and then we'll switch to kinetic friction if we need to. So as we did before, we will add these two equations, and I'll go ahead and plug in. We have the normal forces. The normal force in each case is balancing out the vertical component, or the perpendicular component of gravity. So I'll go ahead and put those values in as well. So that's the coefficient of static friction times the normal force for the first block. We see that this is the second term. Tension and tension cancel out again. We have the other force of friction that we will include. And what we see here is we have force of gravity pulling us down on the right side of the system over here. We have to pull the right side down, we have to pull the left side up, and we have to overcome gravity for both blocks. So these are our external forces. We have external forces due to gravity, one for each block. We have external forces between the block and the surface, which is the force of friction in each direction. The internal forces, which is tension, has canceled out in this case. And so what we can find here, to find acceleration, we will factor out the common acceleration. And what we'll end up doing is have the acceleration as a very large fraction. And what we're seeing here is that that force, the gravitational force, acting on M2, the heavier block, has to be strong enough to pull the other block up and to break the force of friction with both of the between both blocks and the surface. And we'll see if that is possible. We can find the acceleration here when we plug in the amounts. What we get here is a negative amount. The negative amount typically tells us that the acceleration should just be in the opposite direction of what we said it ought to be in. But we already found out that the acceleration, if there is any, has to be in this direction. And so what this is telling us is here we're assuming the maximum value of the static friction. And what this is saying is that if we had the maximum value of the static friction would be strong enough to actually drag the blocks back over and push them the opposite way. Of course, it doesn't actually make sense for the friction, for an inanimate object to be dragging blocks along its face. So what that means is actually a smaller than the maximum value of static friction is sufficient to make the acceleration actually equal 0. And so in this case, our acceleration, we can conclude, equals 0, because we found the direction that the acceleration had to go in, and then when we tried to find the amount of that acceleration came out being negative again, and that doesn't make any sense for us. That means that the static friction has to be less than the maximum amount, but that's still enough to totally shut down all the motion. If we had found that the acceleration was greater than 0, what that would have told us was that we are indeed accelerating in the direction that we ought to be going. If that's the case, even if we have an acceleration, even in the case of having the maximum possible static friction, that means gravity is enough to break static friction. What we would have done is switched this mu s into a mu k. That would have reduced the drag on our acceleration, and our acceleration would end up being a slightly larger number. I'll look at the other exercise, and you'll see an example of that. Exercise 4D.